Greetings, folks. We're live. This time, hopefully in higher resolution. Hello to everyone who is watching back later. And welcome to everyone who's on the stream. If you're joining now, just drop in a comment, say hello, and let me know any questions. I might be able to get them during the live stream as I work through the project today, which is part 2 of building transformers from scratch. We're going to be continuing on building a weather prediction model where we're trying to predict the weather for tomorrow, or the temperature for tomorrow. Howdy, Yugi. Thanks for saying hello. Last week, we got a first transformer made with the help of ChatGPT, and we'll be continuing on from that today, feeding in a real data set of temperatures, so 32 temperatures, and trying to predict the next temperature based on a history of 32 temperatures. And we're going to pull data in from the last few decades for Dublin and see if we can build a model to predict the weather for tomorrow in Dublin. Hey, Christian, how's life? So I'm here in the Colab notebook that I'm going to share. Let me do that now. I think I need to make it shareable. And you should be able to follow along then if you wish. I'm just using a free Colab GPU. So let me set it to anyone with the link and drop that into the chat here. So yeah, if you head over to the chat, you should be able to grab that link now, and you'll find all of the links about this broadcast, about Trelis. So I think we're ready to get started here. And I'm going to just go through what I did last week. There are a few points I want to talk about. In particular, I want to clarify encoder versus decoder as an architecture. So I'll talk about that with reference to the attention is all you need paper. I want to talk a bit about rope versus sinusoidal embeddings. That came up last week. This is where you're trying to add positional information to tokens. So tokens, of course, are converted into vectors, but you also need to add information on where that token is in the sequence. So I'm going to talk about the two methods of rope and sinusoidal. It'll be pretty brief and graphical, so don't worry about getting too mathematical. I'll talk briefly about pre-norm versus post-norm. The original transformer uses a post-norm method, but since then, pre-norm has been found to be more stable. I'll explain that. And then we're going to add a real data set for weather in Dublin and actually train the simple transformer model. And we'll evaluate the performance, see if it's able to predict a reasonable temperature for the weather tomorrow. So let me just pull up here, the attention is all you need. In the PDF on archive, because I want to just show the graphic. And that'll help us to visualize again what we're building. So there's this, I don't want to open Safari. So here we have the transformer architecture that is from the original 2017 paper. And we are using this architecture to predict the temperature tomorrow based on a history of 32 data points. And what I want to clarify here is the difference between an encoder and a decoder. So what an encoder does at a high level is it takes in inputs, for example, a series of temperatures or a series of tokens if it's a speech model, and it will convert it into vectors. And those vectors, as they go through layers and layers of a transformer, which will be attention and multi-layer perceptrons, those vectors are going to be shifted in space and direction and length as they interact with each other. So that's an encoder. It goes from some information like numbers or text into vectors. Now, a decoder, by contrast, it's going to take vectors and convert it to some kind of useful output data, which could be voice, it could be text. Now, when we talk about GPT, we are typically talking only about decoders in the sense that we have just one set of layers. We have one stack of layers, and we use that same stack of layers regressively for all of the inputs. So when we add on a new output, let's say we're taking a sentence like the quick brown fox, and the next token we predict is jumps. So we predict jumps, then we just add that token, and now we put that full sequence back in again to the decoder here. So we regressively use the same stack. We don't have two separate parts. Now, in some sense, originally, it was more common to have one part of the transformer to deal with the inputs, and then you would only feed the outputs through here. Actually, there's a model called FLAN T4 from Google that uses that kind of architecture. So if you examine FLAN T4, you can look at it on Hugging Face. You can just check it out here. Hugging Face, FLAN T5, sorry, T5. If you look at the T5 model, you'll find it's an encoder-decoder architecture. So it takes in a sequence of text, and it will use the encoder here, which has got its own transformer stack. And then it will start off by feeding in just some kind of start token, like S, something like S between brackets, as a start token for the outputs. And then it will regressively generate outputs. So it literally has a separate transformer stack for the inputs and the outputs. And this is not what GPT typically does. It will just do away with the whole encoder part for the inputs, and will use a single stack for processing everything regressively. Yugi's asking here, is it regressive versus autoregressive? Well, I guess they can both be used autoregressively. It's just that if you do encoder-decoder, you have a dedicated part just for inputs. So let me just bring this back to where we are on training this temperature predictor and what we want to do here. So we have a series of inputs, and they're going to be down here, and we're going to encode them through a transformer stack into a series of vectors. And those vectors then need to predict a temperature. So if we have vectors coming at the output of our encoder stack with some dimension, I think 64 is what we'll be doing today, we're going to need to transform that dimension of 64 back down to 1, because we need to get to an output predicted temperature. So what we're going to see in the design for the temperature prediction is we're going to have this transformer stack taking in our inputs, the temperatures, and then we're going to set up a decoder that's going to predict the temperature for the output. So that's the way that we're going to set it up. We could actually set it up using a decoder only type architecture, where we take in all the temperatures, feed them through a single stack, and just predict the output one. But we're just going to do it the way that we have it set up originally from last week, which GPT basically proposed. And that way is an encoder stack followed by a decoder. Now, just to highlight, whether you're talking encoder or decoder, the stack architecture is typically the same. It's attention and MLP. The difference is how you're handling the inputs and outputs. Okay, so with that kind of prelude on encoders versus decoders, I'm going to quickly go through some of the code we came up with last week to predict the next temperature in a series. And after that, we're going to start putting in some real data. Just a quick question here. Multimodal, like GPT-4o, still a kind of decoder only transformer. Yeah, we don't know the exact architecture of GPT-4o. I put a tweet up on it speculating what it might be on X. I suspect it's mainly a decoder, but it may have a vision encoder tacked on in order to convert the images into features that are fed to the language model, much like how Lava works. And potentially there's also an encoder for the voice. So the voice is getting transformed into vectors through a few layers of an encoder before it then goes into the large kind of text model. So I'm not entirely sure. If you're building Lava, that's what you do. You take a vision encoder and you tack it on before a language model. That's a vision plus text model. But potentially, if you're training from scratch, you could maybe do away with a lot of the encoder and just convert from your audio into some very simple raw features and put them right in. So you can maybe check out the tweet if you like. So causal model it can be implemented with encoder and decoders. And to some extent, if you include an encoder, like here's where encoder makes sense. If you're translating, potentially, now GPTs with decoder only, they work well with translation too. But in theory, you would think that encoder decoder makes a lot of sense for translation, because you have one stack that takes the processing for the input language, say French, and then you have an other stack that deals with English. So I think this is a lot of the intuition around why, well, maybe we should have encoder decoder, because we've got this sequence to sequence type transformation. The drawback, I think, of encoder decoder is you've two stacks. So you're kind of doubling up the amount of weights. And the nice attribute of decoder only is, yeah, you can just train all of those weights in the one stack at once and save having to have the encoder. So my sense is that it seems intuitively nice to separate the function for encoder and decoder, but in practice, the decoder seems to work very well. Okay, so let's take a look at what an encoder looks like with a head on the end to bring us back to one output feature for temperature. And as a reminder, there is the prompt that we used for creating a transformer for predicting the next day's temperature, giving an input sequence. I'll just increase my screen size a little here. And we've included some descriptions. We're using an embedding dimension of 64. So we're going to convert the temperature information into a 64 dimension vector. And we're only going to consider a history of 32 days of temperatures. And you'll see later, I'm going to use the high temperature of each day. So we're going to train to predict the high temperature of the next day. All right, we've also asked GPT to come up with a dummy data set, just so that we can load up the model and we can kind of train it just to check that it's running before we load a real data set. So then we come to our code for generating the dummy data, and we're generating here 64 samples, so 64 rows with 32 inputs each. And notice that my dummy data is not completely random. I'm constraining it to temperatures between 0 and 20, which is kind of representative for Dublin. And so you'll see actually the training loss for that reason will actually fall, because we are, even with dummy data, constraining the outputs of the model. So I'll just run this cell here, which is setting up our training data. And I'm going to print out the data in one of these rows. And here we have it, a tensor that should have 32 data points within it. So it's got 4 times 8, so 32 temperatures here. And there are 64 of those rows in our test, or rather our dummy set. So next up, we come to the transformer design itself. And in the transformer, we're going to need to convert the temperatures into some vectors, which is called converting them into embeddings. And those embeddings need to capture the information about the temperature and the position in the sequence. So is it the first temperature, the third, the fifth? Then we're going to flow into a layer, and the layer is going to have a tension and a feed-forward network. So first, let's just review the embeddings here. And it's actually easiest sometimes to look at the transformer model itself and scroll to look at the forward method, because this explains the steps that you're rolling through when you run forward through the network. And you can see it laid out clearly here. So the first thing in the forward is the embedding. So you convert the source vector into an embedding. So that's going to expand it up to 64 dimensions. Then you have the position encoder, which is adding positional information. So it's saying we're first, we're third, we're fifth. Then that vector is going to be passed through the transformer encoder, which we'll see more on up here. And then it'll finally go through the decoder. And the decoder is really simple. It's just a simple linear layer that brings the dimension from 64 back down to 1, which is our output temperature prediction. So you can see here, if we scroll up a little bit, the decoder is defined as a linear layer, and then linear, and it goes from a dimension of D model, which is 64, down to 1, which is our output dimension. And likewise, you can see the definition for our transformer by scrolling up here. So the transformer is defined as NN transformer encoder, and it's being defined with a certain number of layers. And actually there is detail of how the transformer encoder layer is defined right here. It's specified by a few parameters. So this is a wrapper. I did mention that last week. The wrapper abstracts having to write out the detail of attention and the multi-layer perceptron. It actually would be nice to write that out in raw form. I'll maybe do it at the end of this. But this is a wrapper, so it's handling the attention setup and it's handling the MLP setup. But it is requiring us to give in the dimension of the model, the number of heads, the attention heads, the dimension of the feed forward, dropout. So it's going to randomly turn off some weights during training to avoid overfitting. So this is kind of a nice little bonus feature here that helps overfitting or reduce overfitting. We need to set the activation function, typically relu, silu, gelu. They're all different forms of functions that will provide the neuron type behavior of kind of turning on or off. And we then have these two different settings here, one of which I want to talk about is the norm first versus pre-norm versus post-norm. So I do want to make a few comments on that. And I also want to make a few comments on the choice of the positional encodings, because the positional encodings we're using are rotary, and I want to discuss the difference between rotary and sinusoidal. So let's start off actually and describe this norm first here. What does that mean? So this is a parameter to do with setting up the transformer layer, and the transformer layer is this box here. So it's the combination of attention and feed forward. Now you can see in this graphic, which I'll zoom in on a little bit more, you can see how there's this multi-head attention followed by add and norm. So add and norm, what's happening here is you're taking in a vector, you're taking X around here, and you're adding X, the original value, to the transformed value of X that went through multi-head attention. So basically whatever went in, you're just taking its value and adding on the transformed multi-head attention part. And then you're doing this add and norm. Now, as a reminder, the reason that you add this X value is for stability in training. It means that you've always got flowing through the original vector's value. So even if your transformation is a bit crazy, at least you have the main value that flows through too and kind of stabilizes training. So this is called a skip connection. And then here we have add and norm, where we normalize the addition of this skip connection X plus attention. So this is called post-layer norm. It's post-layer because if you consider this as the layer, you're doing the norm after. And likewise, this is post-layer norm here because you're doing the normalization after the feed forward, which is the multi-layer perceptron typically. And one change in the transformer is that typically this norming is done not on the combination of the skip plus the feed forward, but rather it is done solely on the feed forward values themselves. And it's actually easiest if I explain this just by showing a very quick snippet here from our friend ChatGPT. Let me just head over to the chat I had earlier. So yeah, attention layers are used in encoders and decoders. Yeah, exactly. Like you can see here in the encoder, you've got attention. You've also got it here in the decoder. And here, yeah, that's right. So in the case of our decoder, so we've got an encoder that's kind of processing the information about temperatures. And then at the very end, we just have a simple decoder that's taking that processed information. Let's see it right here. And it's squeezing it back down to predict a temperature, down to dimension 1, which is the output temperature we expect. So just a quick note here on feed forward. I'll show you the difference now. So here's an example of pre-layer norm. You've got Y equals X, the skip connection, plus feed forward of the layer norm. So you're basically layer norming the input and then taking the feed forward. Whereas in the post norm, which is the older method in the attention is all you need paper, you're taking the norm of X plus the feed forward network. And this tends to be less stable. I think the intuition for why this is less stable is because you're adding in X to the feed forward representation of X. If your feed forward network is crazy, if it's kind of going wild, then this combination here is going to be wild, and norming it is going to help. But you're going to be norming something that has something wild within it. Whereas if, on the other hand, you separately norm the thing that is wild, which is the X here, this can allow you to, even if this thing here is crazy, you've kind of still preserved X, and this is kind of preserving the stability flowing through your network. So in any case, the fact that we have set this to true, norm equals first, means that we're doing the norm before. So unlike this paper here where it shows the norm after, we're actually doing a norm before we go into the multi-head attention, and then preserving the skip connection X and adding it to the output of multi-head attention. And it would be the same in the feed forward case here. Okay, so that's the pre-norm. And the last thing I want to explain before moving on is this idea of the positional encoding. So we talked last week about how we need to represent somehow the position of where each token is in the sequence. And there are two approaches, one in the original paper that's called sinusoidal embeddings, and there's a more recent approach that's pretty much the main approach now that's called ROPE, which is rotational embeddings. I can just take down this comment here. And I've made a little graphical illustration of how these differ, because I think that's really the only way to get a good understanding on it. So let's check out this notebook, and you can just click it in the link within your own notebook if you want to see it. So I've made up a little script here, and I've made some graphs at the very end. So let's imagine that we have a single token, or in this case, it could be a temperature, all right? And we convert that token into a vector. That's what the embedding process does. It converts tokens or any information into a vector. Now, the simplest vector you can think of, I guess, would be a 0D vector, but let's consider a 2D vector like this. So here we have a base embedding. So this is after you've embedded some kind of information. And what we want to add now is positional information. So we want to do something to this vector that is going to be systematically the same. So the model recognizes, oh, I see the vector and I see it's kind of in a certain position. So I know that must be, say, the third token as opposed to the fifth token. So here's the idea of a sinusoidal position encoding. Basically, you take your original base embedding and you add on another vector to it. This vector here in green, okay? And the way you generate this vector in green is you make its rotation depend on the position in the sequence. So if your token is halfway through your input sequence, maybe you rotate it like this. If it's in like third position, maybe you rotate it like this. So the further your token is in the sequence, the more this vector is going to be rotated. And so in that way, by just kind of naively adding this positional encoding onto your base encoding, you get this combined vector. And so this is how sinusoidal embeddings work. You, using cosine and sine, you set up rotations based on pairs. So all of your embeddings, if you have 64 embeddings, you set it up into pairs. That gives you 32 pairs. And for each pair, you make a little rotation that's proportional, that's going to be proportional to the position in the sequence. And you just add it on. That's how you get sinusoidal embeddings. Now, ROPE is kind of similar, but it's kind of different and better. So here's how ROPE works. You take the base vector in blue, it's the exact same vector, but instead of adding a vector to it, you're going to rotate the actual vector that you started with, and you're going to rotate it by an amount that depends on the position. Now, do you see that? Yeah, so it's simple vector addition. Yes, it's simple vector addition in the sinusoidal case. So you create a vector. When you create this new vector, you position it according to the position in the sequence, okay? And then simple addition. Yes, simple addition. But in the rotational embeddings, or ROPE, it's not simple addition. There's no addition. Rather, you are rotating the vector itself in order to get it to where it needs to be. So you see, it's kind of a subtle difference. They both involve rotation. They both involve cosines and sines. They both involve splitting the embeddings into pairs. So, you know, pairs along your 64 embeddings, 32 pairs, they're all going to be split up. But in the ROPE case, you actually rotate the original vector, whereas in the sinusoidal case, what you do is you just add a little vector here. So yeah, the thing that is probably better about ROPE is you can see that if you just arbitrarily add, yes, the model will kind of learn that if there's this certain amount added, that's kind of related to a position as opposed to being related to token information. But when you rotate, it becomes a bit more clear, it's more descriptive, and it's more differentiated that this is positional as opposed to the raw token-based information. So I think for that reason, you kind of get better performance with ROPE than you do with sinusoidal. Now, there's one other thing to mention, which is that because you're not in 2D, this is a 2D vector, it's actually a 64D vector in our case, you actually have 32 of these graphs. You have 32 of these graphs. And you're not just going to do the exact same thing in the 32 graphs. What you're going to additionally do is you're going to scale the rotation differently in every graph. So in the early graph, you're going to do some kind of low frequency, like maybe going from the start of your sequence to the end is one full turn. But maybe by the 32th, like the 32nd one of these plots here, your rotation is going to be very sensitive. So maybe actually you'll do a full rotation for moving just one position. And what this does is it adds frequency information you're basically adding information on a frequency basis. And yeah, that scaling factor is affected by what's called rope theta. So you'll hear people talk about rope theta. There's also a scaling factor in sinusoidal embeddings, because you have the same thing. You have your 32 maps, if you think about it that way. So you'll hear about rope theta and what value should rope theta be. And rope theta typically needs to be larger. You need to scale across a wider range of frequencies if you're dealing with higher context lengths. So if you see people trying to extend the context length of a model like Llama 2 or whatever the case, you'll often see they increase the value of rope theta because they're trying to expand the range of frequencies basically that are being captured by the positional encodings. Okay, so that was a bit of a diversion, but hopefully an intuitive one. And with that, we're pretty much ready to move on and try to run this model. So we've generated our data. Let me just check the chat here. I'm actually going to plug in my phone. Give me 1 second. Back in a second. I just need to get a lead from my phone because it's going to die, and that's my camera. Okay, and we're in business. So we've got the positional encodings here. And you can see that, first of all, we just calculate the position, which is literally a list going from 0 up to 31. And we then set up an exponential term here. And here you can see the rope theta actually appear. So this is basically splitting out. It's splitting out those 2D maps I talked about all the way across the 64 dimensions. And then we have a sine term and a cosine term because we're rotating in a 2D space. And this is basically how we do the rotation. So when we go forward through the positional encoding, we just take the original vector and then we add on here the positional encoding effect here, which is that rotation that we want. So now, taking us through the transformer model, we have the embedding layer, we have the positional encoder, then we have the encoder layer, which is repeated a number of times. It's going to be repeated n encoder layer times. I think I set this up as an 8-layer model, something like that. And then we have the decoder, which brings us back to one output predicted temperature. And this here just initializes the weights. And you can see here, we're choosing to initialize some weights as uniform, and some weights here as 0. The biases are initialized to 0. So again, last recap, in the forward method, we embed the temperature information into vectors. We then rotate to add positional information. We then go through 8 layers of transformers, and then we decode and get out to one predicted token. And that's the output. So actually there's just one output from every time that we pass forward through one input position. And that's the model. And you can see us initialize it here. We're going to have an input dimension, D model. So I said 64 embeddings. I'm going to choose 8 heads. That's coincidental. It's the square root of 64. Just picked 8. 8 layers. Yeah, I was right about that. And the feed forward. So feed forward is the multi-layer perceptron. It's what you can see here in the feed forward. Basically, we go from 64 dimensions up to the feed forward dimension. So we expand, then we run an activation function, and then we shrink back down again to 64. So if you want to put more nuance, you would make that a larger value. So we're expanding by a factor of, I think that's 4, from 64 roughly up to 256. Yep, there's an activation function and it's ReLU. You can see it right here. So we're expanding to 256, then ReLU, then shrinking back down. I think the question here from John, does this apply for context windows of 1 million tokens? Yeah, so when you're trying to expand the context window of a language model, you typically do need to cover different range of frequencies. And to cover that wider range, you typically will increase your rope theta. So it basically spreads out all of those 2D plots so that they all operate at a wider span of frequencies. So like this one here is going to be going really slowly, and this one at the other end is going to be whirring. And the difference in frequency between those, you want to be larger with a larger context model. Okay, so we have here the model, and we're going to initialize it now. And this is all working fine. We are getting some warning here on nesting. It's basically saying that we would like to enable nesting, which is a computational feature that PyTorch is trying to use to speed things up. But that's affected by the fact that we have used the pre-norm. So the pre-norm is basically, it means maybe we can't be as optimized as PyTorch would like us to be, but this is a really small model and it will run really fast. So that's not going to be an issue. Okay, so what I'm going to do next is I just want to run forward through the model. And this is often a good idea. Just try and run the forward method, which means take some batch of inputs. And the batch of inputs I want to create is just ones. So I'm going to imagine the temperature in Ireland for 32 days in a row was 1 degree C. It's probably pretty unusually rare, but that's basically what I'm saying here. Let's create a batch with 1 row, 32 entries. And it just has a dimension of 1 because there's just 1 temperature per position. So we make up a tensor, we throw it onto CUDA. I am connected to a GPU, and then we forward pass and we get the outputs. And then we print the output, and that should give us the predicted value, which has changed, which makes sense because I just reinitialized the model. So it's got different random initialization. And so with a completely untrained model, if we put in a series of ones, the model is currently coming out with a value of 1. Okay, so that's pretty good. I will notice, I'll note one thing. There are 2 modes typically for a model. There's eval mode, and you can either turn that on or off. And when you're in eval mode, you normally want to turn off the biases. So you don't want to randomly turn on and off neurons when you're actually evaluating a sequence, but you do want to have the biases randomly, the dropout, I should say, not biases. You do want to randomly drop out neurons during training to avoid overfitting. So typically you want to turn off eval if you're going to do any inference, and we'll see that a bit later. I'll explicitly stop doing eval I'll explicitly turn on eval. Okay, so next we're going to move to the training loop. And again, this is largely from last week. I have made one main change. So last week I ran a lot of epochs, like about 10 or 20 epochs. But it turns out the model converges really fast. So I needed to zoom in on one of the early epochs just to see that curve. So what I've done is I've made sure that I'm getting plotted information within a given epoch, and also even doing evaluation within the epoch. So I can just run one epoch and see more granular charted data. So here we are, we're just going to iterate through the epochs with the training. And I'm going to specify later that we'll just train for 1 epoch or 1 or 2. And when we're doing the training, there are a few things that happen. The first thing is you forward pass through the data. So this is just a standard forward pass through the model. Then you calculate the loss, and the loss is going to be whatever temperature we predicted versus whatever temperature the next day actually was. And this is determined by the criterion. The criterion often in a language model will be cross-entropy loss, because you're comparing the predicted token probabilities with the actual. But our criterion is a bit different because we're going to be trying to predict a temperature. So here, if I just copy paste criterion and then I search for it, you see it comes up here as MSE loss. And this is a mean square error loss. So it's simply looking at the mean square error between the predicted temperature from the model and then the actual temperature that is from the next data point. So imagine a sequence of 32 temperatures. The prediction is going to be compared to the 33rd temperature. So actually we need at least 33 temperatures, because you need 32, that'll be for the training, and then you need that actual prediction. That'll become relevant later when we set up the data set. So we forward pass, we calculate the loss with the mean squared error, And then with that loss, the optimizer will propagate backwards and it will calculate the gradients. And then the optimizer will take a step forward. So it's going to move the state of the model a tiny step in the direction of those gradients in order to minimize the error. And then we'll move on to the next step. So this is what's happening in training loop, forward pass, calculate loss, calculate gradients, and take a step with the optimizer to move along the surface of the optimization. Now, once we have done a certain amount of training steps, you can see here. So if the number of training steps are within a certain validation interval, and basically what I'm setting up here is I want to run evaluation every quarter of an epoch. So every time there's a certain evaluation, the model will be set to eval mode. That's what I talked to earlier. It turns off the dropouts. So there's no random neuron being turned off. And then it does a forward pass to calculate here what the validation loss is going to be. So this is very much like what we're doing in training, except you can see when we do evaluation, there's no backward pass. We're not updating the weights based on the evaluation set. We're simply trying to measure if the validation data is improving in performance, and we're not just overfitting the training data. So with that, we have some code here to print out the validation loss. And then I'm plotting out here the training and the evaluation. So let's actually run this. We're going to be running with an optimizer of Atom W, which is atom with weight decay. And the learning rate is quite high. It's 1e minus 3. Probably could be even higher because it's such a small model. So I'll set up that cell there, and then we can run the training loop. So let me just take one or two questions before we do that. Do research teams use frameworks like Lightning, or every team writes their own training loop? Yeah, I think teams do use Lightning, or they use the Hugging Face trainer, for example, like SFT trainer. That's the most common trainer that I use in all of the scripts when I'm doing ORPO, and a lot of the data management is handled automatically. You can also set some pre-defaults. You can set some defaults like, do you want a constant learning rate or a cosine decline? Honestly, it's the data handling that's made a lot easier. But even here, we're using a data loader, which is a wrapper that automatically will kind of batch up the data. You'll see that a bit later. So we're already using some wrappers like you saw earlier. We're using a transformer wrapper. We're not designing from scratch the transformer with attention and MLPs, although I'll show you that a bit later. So yeah, I would say generally teams are probably using trainers, especially if it's a language model, because all of these wrappers don't really change. Where it becomes relevant to do things a little more custom, like what I'm doing, is because it's a bit more of a custom use case, like predicting a temperature. Or if you want to develop a biology model, like there are probably some standard biology models, but maybe you have a use case that you want to size the transformer a bit differently, so you can use PyTorch. Yeah, and I mean, PyTorch is already quite a friendly wrapper on top of Python. It's allowing you to do a lot with pretty short commands. All right, so we'll run this training loop. Sorry, actually, Yugi, you had a question there as well. Can we use seeds to get the same initial weights? Yeah, you probably can set up seeds if you want to keep initializing, or you could save the model and reload it, I guess. So I'm gonna train this now just for one epoch, and yeah, it's like really fast. Let me zoom out because we're not able to see anything. And here's the data. Remember, this is dummy data, so it's not very meaningful. We are seeing a loss fall. This is because our data is not totally random. It's between 0 and 20. But then you can see it's, just oscillating around somewhat noisily. The val loss is not falling anymore. But this tells you that there's something that is fairly sensible about our setup. So we're happy to move on and actually use some real data. So for this, we're going to use Meteostat. I'm going to speed up a little because I see the time here. Meteostat allows you to grab data, and it will grab it for Dublin, which is this specific point here. And it will create a data set involving temperature, average, minimum, max, precipitation, of which there's very little in Ireland. Sorry, there's a lot in Ireland. I meant there's very little snow in Ireland. So you could probably use a lot of this information to develop a better prediction of tomorrow's temperature, but I'm just going to use the max temperature. And we're going to use the MAC temperature from the last 32 days, or in fact, 32-day sequences over the last decades. And that will be the training data to predict tomorrow's Tmax. So as you can see, the Tmaxes are within the range I'd said, 0 and 20. Probably some of them are outside. Anyway, that's irrelevant at this point because we're using real data. So basically at this point, what I want to do is I want to get this data into a format that is going to be matching the dummy data that I have. And I want to just have the Tmax data. I don't want any of the other columns. So I want to get rid of that data. And additionally, I want to make sure that everything is set up into rows of 32 because that's what's needed. I guess that's going to be true if I'm already matching the dummy data. And there's one more thing, which is that every sequence of 32 is always going to have a next value that will be used as the actual value for training, except for the very last sequence of 32. So the last sequence of 32, if it's coming up right to the present day, there's not going to be a data point for tomorrow. So we would need to just throw out that. Now you could use padding, but I'm not going to get into the detail of trying to pad the sequence. I'm just going to take the more raw approach of saying, okay, just discard any data that doesn't have exactly at the end 32 plus then 1 in order for prediction. So what I've done is I've gone into ChatGPT and I've said, and we can try this maybe, I've basically just said, create a data set that matches my dummy set, but that is going to drop all the columns except for Tmax. And that is also going to ensure that every single row has got 32. And additionally, it's going to create sequences of 32, but it's also going to create targets. And the target is a copy of the sequence shifted by 1. So we have a series of sequences and we have a series of targets, which is basically that next prediction value that we need. So that's going to be important to get. And here you see sequence length is all being set up. We set up the sequences, the targets, and also we want to split this data in two. So we want to split it into a training sequence, which will be 80%, and then a validation sequence, which is going to be the other 20%. Now here, to ensure reproducibility, we have set a manual seed. But yeah, as Yugi is pointing out, if you want it to be fully reproducible, you also need to initiate the model in a reproducible way. So that would be a requirement too for full reproducibility. And with that, we are going to set up the training data loader. So you could do this manually and set up a loop that's basically during training going to grab sequences of 32, but using the data loader is a little bit handier. It's a lot handier when you start to do things like padding, or if you want to do operations on the data programmatically, using the data loader is going to be a lot easier. In this case, it's probably not essential, but yeah, I'm going to use it because I think in most cases you would. Notice how there's this shuffling parameter at the end. This will shuffle the data every time that it's loaded. So again, if you want to be reproducible, you probably want to make that false. On the other hand, it can be good to shuffle it, because what you might find is there are certain patterns between sequences that you don't necessarily want it to learn. On the other hand, it might actually kind of be beneficial to train it in the actual sequence that the temperatures appear in the real data set. So there are probably reasons for and against shuffling. I don't really think it'll make much difference. So I've set it true for training. Actually, I didn't even do that. ChatGPT did that when I set up the data loading. Does data loader work for distributed training across multiple machines? Yeah, I think that's also a reason for using the data loader. You will need more than just the data loader for handling multi-GPUs though. I have a video on multi-GPU setup you can take a look at, but you need some framework like distributed data parallel, for example. So that involves quite a bit more code as well. The reason why more code is needed there is because you have to sync information around, say, gradients or optimizer states. So it's not just a matter of where to send the data, it's a matter of how do you coordinate the data. Okay, so I'm going to run this cell and print out a row. Now notice as well how I have filtered out any NaN values. So there's a check back up here. just to see that everything is, you can see here a check that none of the values are NaN, because that's going to cause an issue if you try pass those in when the model expects numbers. So it's just drop those columns. That's the simplest thing you could do with them. You could think of an easier thing or a better thing, maybe like averaging the neighboring values, but I just dropped them. And so here we have one data row. It's got 32 data points as we expect. And this represents 32 days of temperature, high temperatures in Dublin, probably during spring, summer, based on this. And now we can rerun the training and see what we get out of the model if we do that. So we've got the model being fed in, the train data, the validation data through the loaders, the optimizer, which has been set up when we ran the test data. And then we've got one. What's the one? The one is the number of epochs. So we're just going to train for one epoch. And yeah, I was just wondering if I ran that new data. Yeah, so we're printing out data at every step. It's probably a bit superfluous. And then we have the validation loss that's been calculated periodically. That's why you can see it appear here. I think it happens 4 times because I set it like that. And then we have a plot of the training loss per step. So again, kind of like the dummy data, I guess we're coming down in loss, but we're getting down to a significantly lower loss than we were just operating on dummy data. Can we go back and see that? I don't see why not. Let's go back and see what the dummy data was. Yeah. So, you know, the loss here is probably somewhere around 40. And now with some real data, the loss is down around 5. And notice how this converges fairly quickly. So intuitively, what's probably happening is it's recognizing maybe some like seasonal pattern or something. And basically it's finding that whatever the temperature was for the last few days is like a good predictor of the temperature for the next few days. So it seems to be catching up with a lot of that very quickly, even with quite a small amount of data here. And you can see here the validation loss. We first calculate it after about 60 steps. So you can actually see it being higher just because the first measurement is here when the model is already pretty well trained. It does get a little bit better maybe, but when you keep training on more data, not really seeing any improvement at this point here. So let's see if this model is any good. And let's do that by running a forward pass on some real data, actually up to today. So we're going to get 32 data points up as far as today, date and time today. And we're going to get the last 32 data points and then try and predict the next one. And we're going to do this with a function called predicts next 7 days. And we're actually going to regressively estimate the temperature for the next 7 days. So let's do something a little more interesting. Predict today, take that, feed it back in, predict tomorrow, and keep going. So 7-day forecast. Got a model here for a 7-day forecast. You can see how fast it is because it's using the GPU with a tiny model. And so, yeah, in Ireland, the high temperature, it has been fairly warm in Ireland. I'm in Dublin, and you can see here 20 down to 17 degrees C, thankfully, not Fahrenheit. And the predicted temperature is coming off of that, you know, 17, 18, 19. It's, you know, kind of reasonable. Let's say Dublin weather. Let's see what it says compared to our model. So here, got Fahrenheit. Let's go to Celsius. So yeah, the actual weather is colder than what it thinks. Although the high is what we're looking at. So it's predicting 17, 19, 18, 18, 18, 16. And here it's like 17, 18, 18, 19, 19. So the temperatures aren't crazy. I wouldn't say it's got a nuanced understanding of the future weather, but I think it's certainly giving something reasonable. If we wanted to improve it, what would we do? Well, we could start off by adding in more input data. So instead of just adding in at every input position temperature, we could think about concatenating some information maybe on pressure. Let's see, is there pressure data in the data set? Improve processing. Yeah, so we don't have pressure. Yeah, we do. So we could think about putting in pressure. We could think about putting in wind speed, wind direction. These kind of these kinds of information, I'm pretty sure if we added them in, would lead to a better prediction of the temperature for the next days, and possibly allow us to get this validation loss in our graph down even further. Where's the graph gone? Potentially also with more data, maybe we'd be able to just keep training on down here for a bit longer, whereas we're kind of saturating with just giving simple temperature information at the moment. Now, there's one other test. I see a question there from Yugi on the volatility, but one question you should ask me is, well, what if you run this prediction without training the model? Is it bad? Or am I just kind of fluking this here somehow? So let's run it without training the model. How do we do that? Well, we can just initiate the model fresh. So let's reinitiate the model. So now we have an untrained model here. And let's go back down and run this forward pass. And here you can see the predicted temperatures are 2, 2.5, 2.5, 2.5. So that's a pretty bad prediction. Like, it would be very unlikely to have a few days with these temperatures in the teens and then down to the 2s. Now, notice how this kind of matches when we fed in a pattern of just 1s. And that's because we're kind of we're initiating weights to these normal distributions. So it's kind of understandable that you just see this fairly boring flat projection out of it, perhaps. So either way, the training is certainly working, and it's certainly adding information to the model, which is giving it predictive power. Now, volatility. Is such volatility in loss graph concerning for training? No, I would say no, not this type of volatility here. I kind of, as a rule of thumb, if you see oscillation in training data in the training curve here, that is like, so if it's maybe 1/2 to 1/3 the height of the graph, so if you had volatility going like literally 1/2 to 1/3 the height of the graph, then I would say either one of two things. One is your batch size is too small, so you need to get better smoothing by either increasing your batch size, or if you run out of memory, adding a higher value of gradient accumulation. That's not the case here. It actually looks great. Like, it's only, a few percent. If you look at any of the training papers, like on Llama 2, actually you'll see way more volatility. Like, literally, it's almost like a solid line of training data that will be often 1/5 or even 1/4 of the height of the graph, and it will very slowly be going down. Now, the other volatility I'd look at is eval. Eval should be a lot smoother because you're sampling it a lot less often as well. And also your eval dataset is typically larger than your batch size. So when you're training, if your batch size is 32, you're smoothing over 32 data points. But when you've got eval, you're usually using like 10% of the dataset. So if you're doing that, you should have way more smoothing. So if you see bumpiness in your eval, that's definitely more concerning. Also, if you see your eval going up, that means that you're probably overfitting. And if you see your training data just going wild, then that might mean your training your training rate, your learning rate is too high. So I don't see any of those things going wrong. So I think this is fairly good. It's just, I'm not really getting extra value for the decades of data that I'm training through here. It's basically got the pattern. This kind of makes sense. Like, there's not any radical difference in the weather between today and between 20, 30 years ago. Like, it's very broadly the same kind of pattern of behavior. John, is there a location encoded in the data set? Yes. So there's certainly nothing that we're encoding. This data is specific to a GPS location. So it is data from a location. And certainly you could improve this model by adding neighboring information. So all we're adding right now is the history of temperatures at one GPS point. So the next thing we could do to improve it is we could add more inputs that include like temperature and pressure. So that would be the next step. The next step after that would be maybe what you're suggesting, which is, okay, let's not just add temperature pressure for this GPS location. Let's add it. Let's add the history for locations around. And obviously that's what, weather prediction tools do. They consider like these whole graphs, or rather maps, of weather, and that helps them to predict then at a more local location. But yeah, I mean, my sense is probably with a simple model of this size, just by taking kind of online data from GPS and adding in a few key locations, you probably could develop a reasonably accurate weather prediction tool, is my guess. And obviously, you know, Google have gone to massive lengths to build highly accurate ones, at least on limited time horizons. You see, once you go beyond, I think it becomes exponentially hard as you go out in days. But yeah, hope that answered your question there, John. So yeah, if you have any more questions, happy to take them. Pretty much at the end here of the tutorial and the series, two-part series. All right, folks, you can find, I'll just throw it up on the screen again. If you want access to this notebook, you can find it here from the chat. You'll be able to get the links also to understanding rope versus sinusoidal embeddings, and also pre-norm versus post-norm. Any other resources you want from Trelis, you can find them at trelis.com/about. And I'll be back here 5 o'clock next week, same time. And Yugi's asking what would be next in bucket? You mean next on the live stream? Yeah, I haven't decided what I'll be doing next week. Next in bucket. Open to suggestions. I'll put up a link after the show so you can comment if you like, either on X with suggestions. Open to those. In the meantime, folks, have a good rest of the week and enjoy the weekend. Cheers.